The following is the final project for Petroleum Engineering 3085, Well Performance and Production, on the Tortuga field case study done by Nathan Black, Maci Constant, Gerard LeBlanc, and Madelyn Perez. Our goal is to model the production history for a fictitious deepwater field, Tortuga, in the Gulf of Mexico. We are given certain parameters such as permeability, porosity, drainage area, oil in place, and some others. Some of the parameters are unknown, and we use formulas and graphs to estimate these parameters to use in our analysis. Based on the information given to us and gathered, we use an Excel program to calculate the production rate and cumulative production for 10 years of the life of the well. In addition, we present pressure profiles from the well and the tubing at a measured depth of 18,135 feet to the surface. We then profile 1,935 feet below sea level to the platform deck, 12 miles away and 82 feet above sea level via a dual line. We first present a base case with certain given parameters, and then from there we manipulate certain aspects of the well, such as choke opening, completions, and others, while holding all other things constant to see the effect that each component has on the production data and pressure profiles of our well. In order to find the pressure profile in the pipe, we must account for acceleration, gravity, and friction in the pipe. In order to get an accurate friction gradient, we obtained a friction factor for our tubing and dual line to the platform. We used the drawn tubing line from the chart in Economid's book to obtain a friction factor of 1.5 times 10 to the negative 5 for our 4.5-inch tubing and a 1.2 times 10 to the negative 5 friction factor for our 5-inch dual line. Our given API gravity of 30 degrees API allowed us to obtain a formation volume factor for oil of 1.4 using this curve fit of formation volume factors with respect to API gravity. In order to form accurate IPRs, we needed a bubble point pressure for our well. Using Standings correlation and given information, we calculated a bubble point pressure of 4,656 psi. Although this number helped us to form IPRs, none of the models that we formed reached the bubble point pressure, making all of our wells entirely one phase. We also needed to estimate an external radius for our reservoir. We assumed a circular drainage shape and were able to calculate an external radius of 4,560 feet based off that 1,500 acres given as the drainage area. To forecast early time production, we needed to find the production of transient flow. We use the above equation to find the time that our well would be in the transient state. First, we need to extrapolate a viscosity of 4.2 centipoise using a pressure of 8,000 psi, which seemed like a suitable pressure in the range of our well. Next, a total compressibility of 4.5 times 10 to the negative 6 was observed using the Petrosky model and an API gravity of 30. The time we calculated for transient flow was about 196 hours. Since this was only 0.22% of the total time of our forecast, we chose to neglect transient flow since the flow coming from this 196 hours would barely be noticeable. To form our IPR curves, we used Dietz inflow equation for pressures above the bubble point. We chose this equation to allow us to observe changes in flow rate due to different drainage shapes as we will observe later. Under the bubble point, we used modified Vogel's equation to obtain values. To find Qmax, we first used the bubble point pressure and flow rate found from the Dietz model to calculate the productivity index J. This gave us the ability to use modified Vogel to find flow rates under the bubble point. All equations are from Economid's, and the Qmax formula is from Lyon's Standard Handbook of Petroleum and Natural Gas Engineering. For our base case, we use the open hole Hawkins formula to calculate a skin of 3.03. This is from an open hole completion with a half-foot wellbore radius and damage length of 5 inches. Our choke is set to a 1/4 inch, and we use all other previously assumed values along with a circular drainage shape to form the IPR seen here. We formed a TPR by using the Excel spreadsheet that modeled pressures in the pipe from the wellhead to the platform, but modifying it to simulate flow from the wellbore to the wellhead by changing flow regime equations and placing the correct parameters in the spreadsheet. An area of uncertainty is here as our TPR and IPR do not cross at the value we achieve for our initial flow. We believe this could be due to the platform spreadsheet not being a perfect model for the wellbore flow. However, the TPR does maintain the shape that we expected to observe from our TPR. The base case and all other cases from here on out contain 2 wells. The following is the production data for 10 years of the life of the 2 base case wells combined. We assume the 5 million barrels of oil in place was for each well, leading to a total of 10 million barrels of cumulative production. The well experiences a steady decline in production and reached its production limit of 10 million barrels at 4.5 years, denoted by the X's on the graph. Although the well would only actually produce for 4.5 years, we continue to plot production data for the full 10 years. We did this to gain better insight into the production decline that the well would experience and to ensure accuracy in our previously obtained results by being able to better notice trends. Throughout the 10 years, the base case wells were entirely single phase, not yet hitting bubble point. The following are pressure profiles for the base case from the bottom of the tubing to the wellhead, denoted by wellhead, and also from the wellhead to the separator on the platform 12 miles away, denoted by platform. The top two pictures are for the beginning of production, and the bottom two are for the end of production at 4.5 years. P2 denotes the pressure on the downstream side of the choke, and PW denotes the pressure at the wellhead. By maintaining a wellhead pressure twice out of the pressure on the downstream side of the choke, we are in critical flow. With this critical flow, changes in the pressure downstream of the choke will not affect the flow rate because the pressure disturbances cannot travel upstream faster than the sonic velocity. Critical flow was experienced for the entire duration of the well's life in our base case.
The first two scenarios we examined were separator pressures higher and lower than the base case. For both cases, the well experienced this critical flow for the duration of the life of the well, at initial, final, and all points in between. Thus, the wellhead did not feel the effects of the higher and lower separator pressure, and there was no effect on the flow of our well. In turn, this gives us the same IPR and production data as our base case since no other parameters were changed in this case. Although the production data did not change, some aspects of the pressure profile did. The pressure profiles for the wellhead remained the same, but the pressure profiles to the platform did experience a change with the lower and higher ending pressure at the separator. For our higher pressure, we chose a separator pressure of 700 psi. Although this did raise our P2 over 200 psi for the initial case, the wellhead pressure is well beyond twice the P2 needed for critical flow. P2, however, did stay higher for the final case than the base case and for most cases we observed. This could pose problems for wells that do have wellhead pressures that would cause the flow to reach subcritical levels. For lower separator pressures, we chose a pressure of 250 psi. It was also in critical flow and had the opposite effect of the higher separator pressure in terms of initial and final P2. We saw a steeper increase in the wellhead pressure drop, allowing the well to stay in critical flow longer if needed. One of the different completion scenarios we examined was the effect of an incline wellbore. The effect of an incline wellbore at an assumed offset of 30 degrees and an anisotropic index of square root of 10 yields a skin of negative 0.71 using Bessen's anisotropic formula. Adding this to our Hawkins skin gives a total skin of 2.32. The IPR experienced an increase in slope due to the decrease in skin. However, it is not much due to the expected small reduction in skin. In addition to an analysis of an inclined wellbore, we also examined the effect of perforations on production. We selected reasonable perforation characteristics. We used Caracas and Tariq's empirical model to calculate perforation skin since the length of our perforations was longer than the damage zone. This allowed us to neglect Hawkins' formula and simply use the perforation skin that we obtained of 8.99. Tripling of the skin had a substantial impact on the IPR's maximum flow rate and slope with all other factors held constant. Although a decent range of skin factors were used, overall they did not have a large effect on production. The skin from the perforations did draw down production a few hundred barrels per day, whereas the inclined wellbore had seemingly no effect. The inclined wellbore took 4.5 years to hit the 10 million barrel mark, and the perforations took slightly longer to close to 4.7 years. The small change in production is most likely due to the fact that the IPRs were similar at high pressures of our well. Once again, the wells remained at critical flow for the duration of the life, allowing the Excel program to yield accurate results. The completion skins did not have much effect on pressure profiles of the wells.
The effect of wellbore radius is seen in Dietz' equation itself, and it is also used in Hawkins' formula to calculate skin. The smaller radius leads to both a larger skin and a larger number in the denominator of the Dietz flow equation. The opposite is true for larger wellbore radiuses as illustrated by IPR curves. Similar to completions, a large effect on IPR did not transfer to a large effect on actual production. A potential area of uncertainty lies here. We expected a large production drop for a decrease in radius of wellbore. However, even reducing the radius to 2 inches did not have a substantial impact on production. All wellbore sizes had nearly the same production rates and times of ultimate well drainage. We once again noticed all flows satisfied the critical flow condition with little change from the base case. Although it is impossible with a 4-inch diameter borehole, we left the 4.5-inch tubing when our wellbore radius was equal to 0.167 feet simply as a comparison to the others. The lack of major changes once again led us to be skeptical of the obtained production results. By far the most substantial impact on production is the opening of the choke. The opening of the choke had the greatest increase in flow of any case, and the closing of the choke had the greatest decrease of any case. We elected to open the choke until we were able to reach the 10,000 barrels per day liquid limit, taking into account the 10% water cut of our reservoir. Opening the choke 4/64 of an inch to a total of 20/64 of an inch allowed us to get close to 9,000 stock tank barrels per day mark for both wells productions. This depleted the two wells reservoirs in just over 2.5 years, a 44% decrease in time from the base case. The larger choke opening did, however, experience a greater production decline than other wells. On the other hand, closing the choke an equal amount, 4/64 of an inch, we saw the production drop dramatically. It took 8 years to deplete the reservoirs, 78% longer than the base case. Opposite of opening the choke, there was a very shallow production decline with a very steady production rate over the 8 years. Although the opening of the choke has a large effect on flow velocities and pressure due to the importance of the diameter on these parameters, both the larger and smaller choke openings were able to satisfy the critical flow necessary for the Excel program. The smaller choke opening leads to a smaller P2, allowing the well to remain in critical flow longer.
Beyond the 4 scenarios required, we also analyzed situations that could affect production to see their potential impact. Using Dietz's equation, we chose alternate drainage shapes to see the impact on production. In addition, the base case had an open hole skin of 3.03, but we wanted to see the potential production increase from induced skin of -7 from hydraulic fracturing or an acid job. Finally, we examined the effects that different tubing sizes would have on the production of our wells. 3 IPRs were constructed for different drainage shapes. The base case was a circular reservoir with shape factor Ca equal to 31.2. We compared that with a 2x1 rectangle with a shape factor of 21.8 and also a 4x1 rectangle with shape factor of 5.38. The drainage shape played little role in changing the IPR. Even for the 4x1 rectangle, the difference is only noticeable at very low pressures. The similarities in IPRs at high pressures prepared us for the results we received. There was a negligible amount of difference in the 2x1 production rate. After simulating the first 2 years of the 4x1 rectangle and receiving very similar results, we chose to neglect it and conclude that choosing different drainage shapes for the Dietz model most likely does not have a significant effect on production. With such similar production to the base case, it is no surprise that the pressure profiles look almost identical and maintain the critical flow throughout the life of the two wells. Inducing a negative skin had astounding results for our IPR curves, as our base case fails to even resemble an IPR with the new axes. A negative skin drastically changed the slope and maximum flow rate of the IPR, leading to the great discrepancy with the base case. The negative skin production did not yield results quite as dramatic as the IPR, but there was a significant increase in production, almost 500 barrels a day between the two wells at the initial production. This led the negative skin wells to reach the 10 million barrel mark more than half a year before the base case, almost an 11% decrease in time. Due to the expense of hydraulic fracturing and acid jobs, a cost analysis would have to be performed, taking into account the company's needs to deem the action desirable. The negative skin caused a great pressure increase in the wellhead for both initial and final production. We believe this is due to the negative skin not needing as low of a pressure to float in the wellbore. It also caused a noticeably larger P2, most likely due to the increased flow rates. Both cases still satisfy the critical flow requirement. The base case assumes a tubing size of 4.5 inches. We decided to alter the tubing sizes to see the potential changes in production from 2-inch tubing and 5.5-inch tubing. Changes were made to the relative roughness using the charts presented in the beginning of the presentation. A roughness of 2 × 10⁻⁵ was used for the 2-inch tubing, and a roughness of 1 × 10⁻⁵ was used for the 5.5-inch tubing. We concluded from this that increasing tube size may not have a substantial effect, barely changing production in this case. However, decreasing the size of tubing 2.5 inches caused a 1,000 barrel per day drop in initial production. It also led to 5.5 years of production to reach the 10 million barrel limit, a 22% increase from the base case. We believe this large drop in flow may be because of a smaller tubing size, choking the well from producing its full potential. Decreasing the tubing size did cause a noticeable change in pressure profile. The smaller tubing size led to a much higher wellhead pressure than the base case, confirming our notion that we believe the smaller size is choking the well. The final pressure profile of the smaller tubing was the closest that we observed our reservoir of getting to subcritical flow. However, the larger and smaller tubing sizes were still able to stay in critical flow to preserve the validity of our Excel program.
Final conclusions are that factors such as completions, skins, and wellbore radius do have an impact on production. However, the largest impact is due to the pipe sizes the fluid flows through. The chokes cause our largest increase and decrease by only opening and closing a 1/16 of an inch. The large changes in production from these is testament to how important the choke can be on production of the wells. In addition, decreasing the tubing size can also have a great decrease in the production of wells, once again illustrating the importance of the diameter of pipes. We hope you enjoyed our presentation. Thank you for your time.